Hello, we are Team 25076. I'm Brock Bailey.
I'm Amanda Whalen.
I'm Aisha Anuhi.
I'm Mohammed Al-Hurz.
And I'm Cameron Morrison. We are all chemical engineering majors, and our project is the Hydro-Desulfurization Unit.
The purpose of this Hydro-Desulfurization Unit is to remove the sulfur from diesel, but first we need to understand why sulfur needs to be removed. Sulfur is a naturally occurring compound in the fuels that drive our lives. When we burn that fuel, sulfur is released and reacts in the air to form sulfur oxide compounds, most commonly sulfur dioxide. In high concentrations, these compounds can cause respiratory issues in people. Sulfur oxides also react in the air to make acid rain, which is damaging to natural habitats and human infrastructure. For these reasons, one of the vital tasks of oil refining processes is to prevent sulfur from being in fuel before it ever reaches the pump.
The goal of our project is to design a catalytic hydro-desulfurization unit that can process 30,000 barrels per stream day of a diesel blend such that its sulfur content is reduced to 0.005 weight% in accordance with government standards.
This is the overall system we've designed as a solution to our desulfurization problem. The system can be divided into smaller subsystems that each address a portion of the problem at hand. First, we have the reactor subsystem. Second is the separation. Third is the amine unit. And finally, we have the stabilization subsystem. Let's find out how each subsystem works.
The first step in removing the sulfur from the feed is to run it through a hydrotreating unit. This is a reactor vessel packed with a cobalt molybdenum catalyst. That essentially breaks up the large compounds found in the hydrocarbon blends. Once those molecules are cracked, the heat and pressure of the vessel allows for the removal of elemental sulfur to be treated with hydrogen and turned into hydrogen sulfide gas, or H2S. Using aspenhysis to simulate the reactor, we found that about 166,000 kilograms per hour of the effluent contained compounds associated with our diesel fuel end goal, and around 2,000 kilograms per hour was the hydrogen sulfide we wanted to separate out in later stages. Let's move on to the second subsystem of the process, the separator.
The reactor effluent is composed of hydrogen sulfide gas, light hydrocarbons, and heavy hydrocarbons, which contain our diesel product. To separate the effluent, we first send it to the high-pressure separator. In this vessel, the hydrocarbons are knocked out as liquids while the sour gas exits at the top. This sour gas is sent toward the amine unit. As for the hydrocarbons, they need to be further separated in the low-pressure separator. Here, lighter hydrocarbons exit to the greater plant's fuel gas system, while the heavy hydrocarbons exit below and move on to the stabilizer system. Let's follow the sour gas outlet first.
The sour gas exiting the high-pressure separator contains three major components: hydrogen, hydrogen sulfide, and light hydrocarbons. The amine unit separates the gas into these components with three goals in mind. First, maximizing the removal of hydrogen sulfide. Hydrogen sulfide is a highly toxic and corrosive gas, so it needs to be removed from the system to be processed elsewhere. This is accomplished by feeding the sour gas into an absorption column and contacting it with liquid MDE amine. The amine will absorb the H2S, leaving behind a clean gas known as sweet gas that exits at the top of the column. The sweet gas contains the hydrogen and light hydrocarbons from the sour gas. A second goal of this unit is to maximize the recovery of hydrogen. This is accomplished by cooling the sweet gas and sending it to a separator, from which the hydrogen is recycled back to the reactor, and the hydrocarbons are sent to the plant's fuel gas system.
You may be wondering, what happened to the hydrogen sulfide? At this point, it is entrained in the MDA, leaving the absorber. To remove it from the system, the H2S-rich MDA is sent to the amine stripper, where it is heated until the hydrogen sulfide boils off into a concentrated acid gas stream at the top of the column. This acid gas is sent to an external sulfur recovery unit, where it will be transformed into an elemental sulfur product. The regenerated MDA, now clean of hydrogen sulfide, is sent back to the absorber, which leads us to our goal of maximizing the MDA regeneration. The more effective the amine stripper is at regenerating the MDA, the less we have to spend on replenishing the stream with new MDA. Optimizing the system in Aspen HYSYS, where we will be achieving 100% removal of H2S from the sour gas, recovery of 99.9% of hydrogen and sour gas, and 98% purity of hydrogen being recycled to the reactor, a 100% regeneration rate of MDA. Now that we've discussed how the sour gas is processed, let's go back to the heavy hydrocarbon outlet of the separation subsystem.
In the final stages of our hydro-desulfurization process, the heavier diesel-rich stream from the low-pressure separator is pumped downstream into the stabilizer column. This stream still contains a mixture of trace naphtha, a mid-weight hydrocarbon, and heavier diesel hydrocarbons, primarily in the 10 to 30 carbon number range. To refine this into a pure diesel product, we need to separate out the lighter components. Inside the stabilizer, we heat the liquid hydrocarbons to 245 degrees Celsius, allowing the lighter naphtha fraction to vaporize and rise through the column. The naphtha exits through the top of the column and is sent to an external isomerization unit and CCR reformer, where it will be used to form gasoline. Meanwhile, the heavier diesel fraction remain in the liquid phase and are collected as the bottom's product. This stream is cooled and depressurized to meet transportation and storage specifications before leaving the unit. This is the final step in our designed process.
We simulated our entire process on Aspen HYSYS and optimized it to achieve our desired product. Let's discuss the final results of this optimization. Of the 30,000 barrels per stream day of our fuel feed, we retained 29,000 barrels per stream day of diesel with a 97% purity. Importantly, the final product meets stringent environmental requirements containing just 0.001 weight percent sulfur, which is way below the 0.005 weight percent limit defined by the ASTM standard for ultra-low sulfur diesel.
Additionally, we found that our process effectively removed 87% of the sulfur content entering into the feed stream.
We've also conducted an economic analysis of our project and estimated a total capital investment of $73 million, with projected annual sales of $920 million. In a real refinery, the costs across units are likely to vary, so it's possible that the profitability of our hydro-desulfurization unit is not applicable to the entire planet.
While our process design was successful in fulfilling its objectives, there are ways to further improve the process and its economics. Since diesel is priced according to its grade, any product existing within the acceptable range of compositions is sold at the same price. In our case, any diesel product meeting the ASTM requirements for ultra-low sulfur diesel, whether it has a 0.005 or 0.001 weight percent sulfur, is sold at the same price. Economically, it's advantageous for a refinery to tune their product to just meet the standard instead of investing more resources into creating a purer product. Therefore, cutting back on our utilities and separation design to bring the sulfur content back up to 0.005 weight percent would reduce costs.
However, this potential for economic improvement should be balanced with safety and environmental goals. The existence of a hydro-desulfurization unit is inherently an environmentally motivated process. Achieving the separation of sulfur from hydrocarbon fuels is about more than meeting government standards or charging higher prices at the pump. It's about achieving a standard for human living, both for ourselves and the generations to come.